Welcome, everyone, to the Innovation Flow podcast, where we break down projects and initiatives that are in our PARC program, our pilot and research program here at South Platte Renew. Thanks for listening today. I'm excited for today's episode. We have two guests on this show to talk about biogas catalytic methanation. And if you don't know what that means, that's okay, because we're going to get to it, and we got experts here to tell us about it. Our first expert is Matt Young from National Renewable Energy Laboratory. Thanks for being here, Matt.
Great, yeah. Thanks, Blair. Pleasure to be here. Excited to talk about our technology and project with you.
Yeah, this is a whole new area I'm dying to learn about here. Our second guest is Bryan Schmerber. He works here at South Platte Renew as a process engineer, midstream process engineer, so deals with our biogas system is one of his main duties. So thanks for being here, Bryan.
Yeah, of course. Thanks for having me.
All right. Well, let me just kick it out and let you guys have the floor and introduce yourself. Maybe you go first, Matt. Tell us a little bit about your background, what you do now, and what you want to do in the future.
Sure. So yeah, I am a chemical engineer by training and also a group manager, which means I get to work with a lot of really smart and motivated people to develop technologies that promote sustainability. And I've historically worked a lot on biofuels, so trying to take biomass and biogenic carbon to make liquid fuels to replace fossil fuels. But what we're working on now, and we'll get into it, is converting carbon dioxide into value-added products. And so what I'm hoping to work on in the future is really working closely with different companies and stakeholders to get the technologies that we develop in the lab kind of out into the marketplace.
Cool. Yeah. How'd you get into this gig? Where'd you go to school, and is this kind of what you were thinking when you were in school?
So I went to school at University of Notre Dame and then Ohio State University. So I picked my colleges based on their football teams.
Yeah. What are the Fighting Irish, and what is the Ohio?
The Buckeyes.
The Buckeyes. That's
yeah.
right. Okay.
So fun to follow this time of year, but both good engineering programs. And so initially I didn't really know exactly where I wanted my education to take me, but I always had a passion for math and science and engineering. And as I was going through school, I thought that sustainability and kind of renewable energy applications were a really neat area, and fit well with my interests. Also with kind of a lot of the work that I've learned about from Bryan going on with South Platte Renew.
Cool.
Yeah.
Well, thanks for being here. All right, how about you, Bryan? What's your story?
I'm also a chemical engineer by trade. I've worked in consulting for about 10 years of my career, doing a lot of industrial process design. So that's more putting together P&IDs, developing...
P&IDs
it's
being...
just piping and instrumentation diagrams.
Okay.
Yep. Sizing equipment and so forth. But a lot like Matt, I wanted to get more into the sustainability and renewable sector, I did a lot of wastewater in the consulting world, so the two kind of came together when I got this job here, and I absolutely love it. And so I am the process midstream engineer here, which means I essentially manage the pipeline injection system, which converts our biogas from our anaerobic digesters, which I'll get into later, into renewable natural gas.
All right, great. Well, let's... we have the icebreaker question before we get into it too much. So the icebreaker question for both of you, what's one misconception about your job or your industry that you'd like to set straight to the viewers or the listeners here?
Well, start. So amongst my friends, a lot of when they hear I'm an R&D scientist or engineer, misconception is that I'm in the lab all day with beakers, kind of mixing solutions the entire day, which isn't true. That's probably only about half of the day. But it is a lot of fun being kind of a professional researcher, because there is a lot of in the lab time, kind of tinkering and trying out new things where you're not entirely sure how it's going to work. Now, it's not like you see in the cartoons where 1 out of 3 times there's an explosion. So certainly that doesn't happen, but you're not really sure what the outcome is of the experiments. So it's kind of a lot of fun doing experimental research.
Yeah.
And yeah, so.
Cool.
Yeah.
Well, would you set your friends straight? Whenever I tell my friends I work in wastewater, they invariably start talking about their toilets. Like, I got this leak on my toilet, and my toilet's doing this. And I'm like, they hear wastewater, they think toilets, and next thing I know, I'm talking about their toilets. So I don't tell many people, keep it quiet. How about you, Brian? What's a misconception about you or your job?
Similar situation, Blair. When I tell people I work in wastewater, I usually get ugh,
Yeah.
and then the conversation ends.
Yeah.
But I think people really don't know what really goes into wastewater. They don't understand the technologies, the innovation, the minds that all go into cleaning the water and what water resource recovery facility does, and all the things that you can take out of the wastewater, nutrients and renewable energy and so forth. So,
Yeah, that's part of the reason we started this Innovation Flow podcast, to clue people into what PARC's got going on and things that are happening at the plant. So hopefully you guys are helping the public, and this podcast helping the public understand that wastewater is cooler than you might think.
It is cool.
Yeah. All right. Well, let's get into biogas catalytic methanation, and I know that part of this is the NREL project, but the NREL project is based on gas produced at South Platte Renew. So if you could just quickly, Brian, take us through, where does this gas come from? How does it get to the end? How does it get treated or go through the process, and where does it come from?
Yeah. So biogas is a byproduct of the anaerobic digestion process, so in a wastewater facility, we remove all of the biosolids from the wastewater, and then we send all those biosolids to an anaerobic digester to get further treated. And in that digester, it undergoes various biological processes to create essentially an inert biosolid, which can be used for land application. And then as part of that biological breakdown of those solids, you get what's called biogas, and it's a gas which is about 60% methane and 40% carbon dioxide. Traditionally, it's flared, but now we've identified the potential of this renewable source. And
By flared, you mean just lit on fire?
Lit on fire,
and
yeah.
It burns it and goes into the atmosphere.
Yep, there's that 60% methane. It's a combustible gas, so you can just flare it, and it methane is a greenhouse gas, and it's like 25 times that of CO2. So that's why you flare it, so you can combust it into CO2. But what we do is we capture that and we clean it up, and then we put it into a pipeline to be used and displace geological natural gas. So.
Cool. Yeah. All right. Well, then that brings us right to Matt. So the gas gets cleaned up, and then tell us your story. What are you doing with it, Matt?
Yeah. Well, kind of at a high level, this biogas catalytic methanation process is built into a concept that they call power to gas. And so, like Brian mentioned, biogas generally has 60% methane, or renewable natural gas, which is a good product that you want to use. And 40% of that gas is carbon dioxide, and it's just vented to the atmosphere and not being used. And so, kind of the motivation would be, would there be a way to utilize 100% of all of that biogas to make renewable natural gas? And so the reason it's called kind of power to gas is with the deployment of renewable electricity, there's two big challenges for decarbonization. So one of them is deployment of renewable electricity, but with the price of solar panels going down, wind turbines going down, there are times when there's just excess renewable electricity, more than the grid can handle. And so the idea is there a way to store that renewable electricity. So that's kind of a second component, the storage. And that's where this biogas comes in. And so the idea is to take this excess renewable electricity or the excess power and store that in a chemical form, which it would be renewable natural gas with this methanation technology. And so kind of describing that a little bit, when there's extra electricity available, like wind and solar, you can power an electrolyzer, and so it takes water to make hydrogen. And hydrogen's a great fuel, but currently there's not really a market, or there's a market, but there's not a good way to utilize and distribute it.
Yeah.
But natural gas, I know at my house, my water heater's natural gas, my stove's natural gas, and the majority of electricity in the United States is generated from natural gas. So there's hundreds of thousands of miles of distribution infrastructure, and so if we can take this renewable energy, turn it into natural gas, it's a good way to integrate with the hydrogen economy to distribute a product and get near-term decarbonization.
Cool.
Yeah.
All right. Well, so that's big picture. Maybe can you dive in a little bit on how you would do this? You get the gas from Bryan, and you take it to your lab, and then how do you turn the CO2 into methane?
Yeah, sure. So there is
Is it that simple?
Yeah,
it sounds pretty simple.
It is. It's, it's just that quick and easy. So this is in this project we're actually working with some researchers from University of Virginia, and they've developed a special methanation catalyst. And I should give a shout out to Professor Sin Zhang. He's kind of the PI. Principal investigator on this project.
All right.
And so he and his team have looked at a variety of methanation catalysts, and but I won't initially get too deep into the science.
Thank you.
Looked at different properties of the metal particle size, so talking about really small to really, really, really small, and it changes, on the order of 10 nanometers to like 2 nanometers, and depending on how large you make it, it affects the reactivity. But at any rate, I said I wouldn't go into the science.
Oh, but now, are you talking nanoparticles? Because now I'm excited. I've heard of those before.
But they're developing a catalyst that is an improvement on state-of-the-art. But when we get the gas from Bryan, ships it over to NREL, we're able to run that through our reactors, load these catalysts developed by University of Virginia, and we test different process conditions to try to basically take a mixture of carbon dioxide, methane, add hydrogen to the reactor, we pass it over the reactor, we vary kind of the temperature, the pressure, and the amount of hydrogen, how fast the gas is going through to change residence time, and we look at what's coming out on the back end. And so ideally, the only products on the back end would be methane or renewable natural gas and water, which is easily separated out. And so we, depending on how you operate the reactor, of course you get different performance, and then that ties into these process models to really holistically look at the energy consumption of the whole process.
Yeah. Maybe can you describe I'm asking a catalyst engineer, but so maybe I'm setting myself up. But what is a catalyst? What does a catalyst do? What does that mean?
Sure. So a catalyst is something that will, so in the textbook fashion, enhance the rate of reaction, and it doesn't get used up itself. It just takes some reactants and they interact with the catalyst and make a product. But what it does well is, so in the case of, let's say, carbon dioxide and methane, you could put them in a tube, heat them up to some high temperature, and they might make some methane. But if you have a catalyst there, you can operate at a much lower temperature, and that reaction can take place very quickly as compared to if there was no catalyst.
Oh.
So essentially it makes things happen much faster and less energy input and cheaper than if it were absent.
Cool. Yeah, it's like little bit of alchemy. It feels like
Yeah.
turning something into gold or something. Can you do that?
I'm working on it.
All right.
I'm working on it.
We'll have you back. If you
Yeah.
figure that one out, we'll have you back.
All right.
Brian, what does all this mean for you here at South Platte Renew? Or what does it mean to a wastewater plant if this carbon dioxide could be converted?
Yeah, it'd be massive impacts. The traditional biogas upgrading systems use physical separation. Essentially, it takes the mixture of gases of carbon dioxide and methane, and the upgrading technology essentially separates those two molecules. Whether it's a membrane or a pressure swing absorption system, you always have a waste gas of CO2. So if we were to be able to apply Matt's technology to the facility, we'd essentially increase our yield of renewable natural gas. So we take that carbon and the carbon dioxide, and we'd actually convert that into more methane rather than admitting it to the atmosphere and wasting that. So if we would increase the yield, we'd increase our revenues. It would also increase the environmental stewardship of the facility as well. It would lower the amount of CO2 we actually release in the air from that. So it would be very impactful to the industry and South Platte Renew.
Cool. So you're sustainable now, but this could allow you to go super sustainable. I mean, get even that 40% that currently you can't do anything with,
Yep.
make it usable, huh?
Yep.
Who thought of this?
Well, I mean, I guess the NREL team first approached Bryan, but we weren't the first people to think about methanation of CO2. There are some, there's examples, especially in Europe, about utilizing either both biogas sources or it could be other CO2 sources and converting. Goes back to the power to gas concept. But we thought. And I was actually reading just a Denver Post article about the work going on at South Platte Renew, creating pipeline injection RNG. And so I know it was already part of the mission to valorize the gas. And so I thought there might be a good opportunity to connect the dots between NREL's research on advanced new technologies and kind of partnering with South Platte Renew to kind of, as you said, go super sustainable, right? Mm-hmm. And even ways to enhance the technology, enhance the decarbonization, let's say.
Cool. Well, I'm glad you were reading that article and put it all together. That's good. I want to get a little bit off topic now, and we'll get back to the methanation project. But before that, I want to ask each of you, who's your science or inventor hero? And why do you like them? So who wants to go first? Matt? Brian, you want to go? Why don't you go first, Brian? Your science inventor hero.
All right. I didn't really have one, but I would say I had to do some Googling. This guy named George Edward Davis. He's considered the father of chemical engineering. And the fact that I've dedicated 4 years of college and the rest of my career to this discipline, I think I have a lot to thank this guy for. He was a chemist. He was a French chemist for industrial process company, and he found out that it was hard to solve the problems in the industrial chemistry application because it was so complex. So he essentially broke down the problem into smaller unit operations, which are simpler systems, and then kind of went from there, and it helped revolutionize the chemical industry.
Cool.
Yeah, thanks, George.
George, what was his last name?
George Edward Davis was his full name.
George Edward Davis. I have to remember that. All right. How about you, Matt? Who's your hero as far as science?
Well, I'll say, and sticking with the Davis theme, I have another Davis, a scientist that I look up to. His name is Mark Davis, and he's a well-known researcher. He's a professor at Caltech and did a lot of work in zeolites, which is a class of catalysts and materials with a lot of really small pores. They're used a lot in the petrochemical industry to rearrange molecules, and he published a lot of great work in that area. And then, he has kind of a little, I think, a personal story, and his wife passed away, sadly, from cancer, and then I think he changed his research focus to be kind of on oncology and drug delivery, and has done phenomenal work in that area, has received a lot of awards, and I kind of remember, kind of mid-career, or when I was like in grad school, he had kind of changed his research focus, and so someone was talking about Mark Davis, the cancer drug delivery researcher. I was like, wait, this is a totally different person than I was thinking about, right? I know Mark Davis who does zeolites. They're like, no, that's the same person. But I find it really kind of a hero because, one, I'm a catalyst guy. He has great work in catalysis, but also that, if you're really motivated and bright and willing to take the courage to reinvent yourself, you can make outstanding contributions kind of in a totally different field.
Yeah.
Yeah.
That's a good story, yeah.
Yeah, and I should mention, you might not know this, Brian, but we have another Davis that works actually on this project. His name is Bob Davis. Happens also to be the brother of Mark Davis, who we were just talking about. So a lot of connections to the Davis
it's a
family.
small world, yeah. All right, well, thank you. Let's get back to the project a little bit. Question for you, Brian, like the system set up to send gas back to the pipeline, right? The XL pipeline. How do you get it? What do you put it in? Container. What do you put it in? How do you get it there? What did you have to do to make this project work?
Yeah. So essentially what Matt's team needs is the actual biogas, right, before it's been converted to renewable natural gas. So we had to identify an area to extract the biogas from our system and place it into essentially compressed cylinders. And the challenge for us is just because we don't operate at the level of the pressures that Matt's team needs for their reactors. So we had to get a compressor that essentially boosts the gas from around 200 pounds per square inch all the way up to like 1,200 pounds per square inch. So we now have a very fancy compressor that we are going to be connecting into our system, and from there it's going to pull about 12 cubic feet per minute of gas and compress it into these cylinders up to 1,200 psi. So from that, we'll be able to just deliver that to Matt, where he can use it for his research.
How does that happen? You throw it in the back of your van, or how do you get it over there?
There are courier, like shipment companies that do that type of work, like hazmat type, who can ship compressed cylinders for you.
All right.
Yeah.
So then it arrives in your lab, and you go to work. What have you learned through this project when doing this lab analysis and through this project?
Yeah, it's there's being able to have like a real feedstock is, I think, critical when you're deploying technologies, and so there's always uncertainty about if you're using a real feedstock versus kind of some model idealized system that you're just mixing in the lab. And so, we've learned that the composition that we're kind of modeling isn't always exactly what's coming out of the plant, that it's really important to remove impurities like hydrogen sulfide, siloxanes, volatile organic chemicals. So we've done some lab work there. I know SPR has a commercial process to do that. And so, kind of testing that, but also making sure there's not residual impurities is something we've learned. And I did, I heard Bryan mention with this new compressor that they're using to boost the biogas pressure to 1,200 psi. That's not necessary for our process. And so, I mean, the 1,200 psi is necessary to get the cylinders to us. But another thing we're learning is, what really are the requirements for how high of a pressure do you need to go? And there are different stages in the process where you might pressurize it, either early or later. And depending on how you do that, it results in kind of some differences in overall energy consumption. So.
All right. Where's the project at? It's ongoing now, right? How long will you be doing this research, or do you know? And how will you know when you're done?
Well, we're kind of in the middle of the project now, and Department of Energy will let us know when this phase is done. We're kind of the middle. We've already demonstrated 100 hours of operation with real biogas to make kind of pipeline compliant renewable natural gas. But it was with a very small amount of powdered catalyst. Think of like a bunch of grains of salt, something like that. But what we're hoping to do by the end of this project is to demonstrate it for longer. So 500 hours of a demonstration, but also with higher quantities of biogas, and then with a catalyst that looks more like something that you would use in an industrial reactor. So we call this a technical catalyst, or like a pelletized catalyst. So it's something that would look more like, I don't know, just like little pellets or like rabbit food or something like that, except to be made out of this nickel-based cerium oxide aluminum material. So don't eat it, rabbits. But anyway, so we'd load that up in a reactor and could demonstrate this performance. And so hopefully that would go a long way to kind of showing the feasibility of a project like this for implementation. And we actually have an ongoing discussion about what could be the next stage of this project, which would be really working with an engineering, design, and construction firm to build out a pilot test unit that could be located, hopefully on SPR grounds, and kind of run this process continuously, integrate with an electrolyzer. And so take it out of our labs and, put some steel on the ground and have a demo unit that really integrates on site with a resource recovery facility.
Nice. Yeah. So taking it from bench scale to more pilot scale at a facility, huh?
Yeah.
That is great.
Facility.
Yeah, our
It's
facility.
at our facility.
PARC, yes.
That's what we're hoping for.
Yeah, you're saying all the right things. It's just what PARC is for. Developing ideas, doing pilot studies, research. So that's great. You kind of went into the technology impacts of this technology on the world. The world besides wastewater. But can you summarize what this science means to, the world, I guess, or outside of wastewater?
Sure. So I think globally, right, there's a huge emphasis and, perhaps moral responsibility, you'd say, to kind of have a sustainable, operate sustainably. And this gives a really great near-term and actually longer-term avenue to harness renewable electricity and store it and then utilize it in a way where the public fluid doesn't have to change behavior that much, right? And so
Still have our gas stoves.
we still have our gas stoves, right? And there's always resistance to not only personal resistance to change, but also just like money infrastructure resistance to change. And so I think this technology has really good potential to get excess renewable electricity into homes, into the pipeline, and facilitate this transition to a circular economy. And so I think this is a great project to be a part of in a way that we can really be impactful in the near term.
Cool. Well, how do you feel about that, Bryan, to know that wastewater is part of research that could shape the whole global energy economy?
Yeah, that's why I love this industry. Yeah, that's why I'm doing what I'm doing.
Yeah.
Yeah, I think it's fascinating and it's great to be part of.
Cool.
Yeah, it's exciting every day. You know, listening to Matt's presentations and the whole research team, it's so interesting to me, and to even just be kind of an outsider looking in, it's a lot of fun.
Nice. Yeah. Did you guys run into any hiccups along the way? Any good stories there? Any cylinders fly off the car or anything like that?
Not yet, but when they do, we'll be sure to let you know. I don't have any real hiccups to share.
That's good. That's good.
Yeah.
When you're dealing with biogas, that's probably a good thing.
Exactly right.
All right. Well, thanks for coming today. This has been interesting, and thanks for sharing a little bit about your research with what are they called? Catalytics?
Yeah, it's catalysts.
Catalysts. That's the word I was trying to come up with catalysts and biogas, and giving us the rundown. I appreciate it, Matt.
Yeah. Well, thank you so much. My pleasure.
And Bryan, thank you for breaking down the system and telling us how it all worked.
Yeah, of course. Thanks for having me.
We are not done yet, though. We have the end of show quiz.
Oh.
Yeah.
Oh.
Are you ready?
Oh.
You guys can tag team this. You can participate on a team. I have some book titles here. All right, and so you have to tell me whether they're real or they're fake. All right.
Oh no.
Real or fake book titles.
Okay.
Go for it.
All right. Number 1, knitting with dog hair. Is that real or
It's
fake?
gotta be fake. That's gross.
You think fake?
I'm gonna go fake.
I'm thinking real.
Real?
I'm thinking real. There's
Okay,
some
Matt,
real.
you are correct.
Oh.
It is a real book. It's knitting with dog hair, better a sweater from a dog you know and love than from a sheep you'll never meet.
Sure. But what if you're allergic to dogs like me? That'd be a bummer.
I don't know. You have to read the book and see what they say. Okay, here's the next one. Big Uppins, How to Survive Life. Big Uppins, How to Survive Life. Is that real or fake?
I gotta go fake. I don't know what that means. I don't know what that
Okay.
means.
I don't know what it means, but I am gonna go real. on that
You're going to go
one.
real?
Yeah.
No, Matt is right again. That
Oh,
is
for
fake.
two.
My son came up with that this morning.
Okay.
I said, what are Uppins? He was like, I don't know.
Okay.
I don't even know if it's a thing. All right.
Creative writing.
Okay, you are ahead, Matt, 2-0.
Yes.
Brian, you got 2 more though. You could. Number 3, everything I know about women I learned from my tractor. Is that real?
Real.
I gotta go with real.
You're gonna go
also,
real? Okay, you're
yeah.
both correct. That
Yeah.
is real.
And farmers seem pretty astute about their knowledge of women. So
Yeah, I want to read it. It's written by Roger Welch. If anyone's interested,
Did you
I'm gonna
also
look it
start
up.
farmersonly.com?
I don't know about that. I don't think so.
gotta read. It.
Okay, number 4. And this is the last one. How to avoid huge ships. Is that real or fake?
I would want to pick up a copy of that, and so I'm hopeful that it's real.
Yeah, hopefully it's real. Okay, Brian?
I'm gonna have to go real too on that one.
You're gonna go real. You are both correct. It is
Oh,
real.
wow.
It was written by a ship captain, John W. Trimmer. And I want to check it out because I'm like, what could it be about? You know? But yeah. Okay, well, I think Matt is the winner of our game. We'll have to get him some lovely prizes from the green room. But thanks again for being here. It's been great having you. And maybe once this project goes to the next phase, we can have you back and talk about that.
Be fantastic. Yeah.
Sounds great.
Cool. Well, thanks for being here. And to our viewers and our listeners, if you're viewing on YouTube, go ahead, put some comments in the chat. Let us know what you think of the program, or if you got any ideas on topics that you'd like to hear, or things you want to see on the show. If you're listening on Podcast Player, please give us a 5-star rating on Apple Podcasts if you like the show. And tell your friends. I mean, we don't have a big advertising budget, so word of mouth is how we're getting the Innovation Flow podcast out to people. So thanks for listening. If you want to get a hold of us, the email is innovationflow@inglewoodco.gov. That's how you can get a hold of me here at the podcast. And thanks for listening. We'll see you next time on the Innovation Flow podcast.